Hey guys, today's lecture is going to be kind of short. It's about batteries and EMF. Just as a heads up, this was discussed yesterday in class. I'm a little bit behind on recording video lectures because, teaching is crazy right now and I've got a million things to do and grades are due this week. So y'all are just going to be a little bit behind, but it'll be fine. I'll get caught up over the weekend and we should all be good. But that aside, let's go ahead and get right into it. First thing up is a little rule I didn't discuss in my current video, and it is about the conventions for current, because those are about to become important. The rule is that current is the flow of positive charge, which is weird, and not really how it physically happens. What physically happens in most situations, especially the circuitry we're discussing, is that electrons are the thing that are moving, because electrons are what's mobile in atoms and not protons. But if you look at the mathematical thing for current, the mathematical equation, wow, sorry guys, it's like 5 a.m. and I'm recording this. So anyway, current is change in charge over change in time. So the direction for positive current would be the one for positive charge. If you had negative charge flowing, that would be a negative current. So it makes a little bit of sense mathematically, and it does have a nice consequence that this means current is flowing from high to low potential, because positive charge goes from high to low potential. If we were using the convention that current was the flow of negative charge, that would mean it would go from low potential to high potential, which is kind of counterintuitive, but that's just due to the way that negative particles move in an electric field. Either way, you need to know that current is going to have a positive direction for the flow of positive charge, which is weird. I don't really like it as a convention, but it's what everyone does, so it's what we got to do. Side note, that's really bad reasoning for doing a lot of things, but it's good reasoning for doing this. Now that you know the convention for current, let's get into batteries and EMF. EMF stands for electromotive force, and it's most commonly written as lowercase EMF, because I read this mostly when I was learning about it for the first time. I always pronounced it as EMF, but it's actually EMF. You say the letters EMF. And EMF is basically the thing that gets the electrons moving. It's the electromotive force. Electrons, motor, motion, force. So it's the thing that is making the current move. And the way that it does this is by pushing it from a low potential to a high potential, which is going to give it energy. And here it says like an escalator. I'll show you a picture of that in a minute. Some examples that provide EMF are batteries. Batteries are what we're going to be dealing with most of the time, but this could also be provided by solar panels or generators. All right, so here's the basic picture of what's happening in a circuit using a battery for EMF. You've got positive charges, which we're just going to use for convention, but that's not actually what's moving. It's the negatives moving the opposite way. But we're just going to look at the positive charges because convention. If you got all these positive charges, they're moving around the circuit. Okay? They're moving around the circuit. And as they move around the circuit, they encounter some resistance because they're jiggling the atoms in there. The atoms are taking away their thermal energy. And by the time they get all the way around the circuit, they're super tired out. They're super dead. They can't really do anything anymore because they have lost all of that energy. Energy here is U in these pictures. So you see it starts off with some large amount of energy, goes around the circuit and loses all of that energy to resistance. So by the time it gets to the negative terminal, it's all tired, dead, can't do anything, has to be given energy. EMF is the thing that provides it that energy. Here it's a battery. And what that looks like is basically the idea of an escalator. The charge starts off at the bottom with a low potential, low energy, and as the battery pushes it through a region of increasing potential, its potential energy also increases. Like if you're going upstairs, your gravitational potential energy, going up an escalator, really. If you're going up an escalator, your gravitational potential energy is going to increase. That same thing happens here with the charge. The battery pushes it from low to high potential, which gives it more potential energy, which means that it can go around the circuit again. And this happens through chemical processes that I'm not going to get into. And in generators and solar panels, it's powered by, whatever the generators run on, like gas or something. Or generators can be hydroelectric, so it could be run by water, or it can be run by the sun if it's a solar panel. But really anything that can give it energy is going to provide the EMF. For a battery, that's going to be chemical processes. But for the purposes of this class, you don't really need to know all of the inner workings of the device providing the EMF, but it goes from negative to positive and provides energy to those charges that have been depleted of energy over the circuit. The mathematical expression for this is super easy. This capital epsilon is EMF. And for this class, EMF is always going to be equal to the potential difference across the battery. That's for an ideal battery because we're going to assume that no energy is lost during the internal processes. But in reality, there is some energy lost there because things are never perfect. And these are slightly mathematically different, but we're not going to worry about that right now. We're just going to assume they're the same. If you become an electrical engineer, then you'll find out all those tiny little discrepancies. But for the purposes of this class, we're going to say they are the same. So I said that the EMF is like an escalator pushing the charge up to give it potential energy, and it does that by pushing it through some potential difference, V. And we use the same equation for that as we did in the previous units, where potential energy, which has the variable U, I understand that some of you may be getting used to that still, U is potential energy, equals Q, which is the amount of charge that you're moving, times the potential difference across a battery. And according to our most recent mathematical expression, you can substitute this EMF for delta V. So the potential energy gained by charge is equal to the charge times the EMF of the battery. So this should allow you to solve some more of your homework problems. There will be another lecture incoming about resistance and resistivity. Probably won't get here till tonight, sorry. But do what you can with this lecture and the one about current. If you want to read ahead in the slides and try to figure out some homework from there, you're definitely welcome to. But it'll be probably tonight before I get that lecture out. Thank you guys for your patience and your hard work. I appreciate you all. Please email me if you have questions. Let me know if you need anything. I'll try to get it to you as soon as I can.